The problem statement from Gate Physics 2020 reads as follows. Consider a 4-bit counter constructed out of 4 flip-flops. It is shown by connecting J and K inputs to logic high and feeding the Q output to the clock input of the following flip-flop. See the figure. So you can see that this circuit has 4 JK flip-flops with their outputs being Q0 to Q3 respectively, and the output of the first JK flip-flop is the clock for next flip-flop, which you can see here. Similarly, the output of this flip-flop is the clock. The input signal to the counter is a series of square pulses, and the change of state is triggered by the falling edge. At time t equal to 0, the outputs are in logic low state, that is all the Q0 to Q3 are 0. Then at t equal to t1, the logic state of outputs is, we have been given this input is a series of square pulses, and at time t equal to t0 we are given that all the outputs are 0, and we need to find the output at time t equal to t1. That is, we need to find Q3, Q2, Q1, Q0, the value of these four. And these are the 4 options that are given here, and this is a multiple choice question with one correct answer, and we need to find the correct one. When solving any type of problems relating to counters, we need to talk about their building block, which is the JK flip-flop. So on the left you can see the symbol for this flip-flop. So this is the symbol. J and K are the inputs and Q and Q bar are the outputs, and a clock, and this J flip-flop runs on a clock. This is the clock, and in this case this flip-flop is running on an edge triggered. You see this triangle, this denotes an edge, and it's a negative edge triggered. So for instance, let's say if the clock is something like this, then the output, this truth table will come into effect only when at the negative clock edge. So you see this is being denoted by this downward symbol here, that only at the negative clock edge we'll evaluate the values of J and K and accordingly update the value of Q if needed. So for instance, let's say we are on the negative clock edge and J and K are 0, then the next value Qn plus 1 is the same as Qn. It does not change. So we say is retained. On the other hand, if at the negative clock edge J is 0 and K is 1, the next value of Q is 0. This is often known as the reset condition. Similarly, if J is 1, K is 0, the value of Q is set to 1. This is known as set condition. And finally, if J and K both are 1 at the negative clock edge, then the next output of this flip-flop, this Q, is nothing but Qn bar. This means this is known as the toggle, because if the next output is nothing but the inversion of the previous output. Now we use these flip-flops and these 4 flip-flops to create a circuit. We have used 4 flip-flops. This is a 4-bit ripple counter. This is the ripple counter circuit, and the Q0 is the least significant bit and Q3 is the most significant bit. It's again it's to emphasize that the output of first flip-flop is the clock of second flip-flop, which you can see in all the 3 cases here. And J and K are set to high. So this means this JK flip-flops are operating in the toggle mode, and this is also referred to sometimes as a mod 16 counter. Why mod 16 counter? Because this counter will count from 0, 1, 2 and up to 15, and then again it will be 0. So that's why, and my mod 16, mod stands for modulo. So when you take the remainder of 16, it will come anything between 0 to 15, hence the name mod 16 counter. In general, if there are n bits in a counter circuit, there'll be n flip-flops. So because each flip-flop contributes 1 bit, and it will be a mod to 2 raised to the n counter. So let's say if there were 3 flip-flops, so this means the maximum value it can be from 0 to 7. This means modulo 8. So mod 2 to the power 3 is modulo 8, right, and so on. So this is just a good thing to remember. Finally, this is the truth table that we had there, and we know that J and K both are high, so only the 4th row, we will be using only the 4th row, and this means that we note that the output toggles at every falling clock edge. So this is a falling negative edge triggered flip-flops, and the output will toggle every time there is a falling clock edge. Now this was the circuit that was given to us, and from previous line we note that this is the output is the falling clock edge. J and K both are high, and the output will simply toggle from the previous state. So for now, let's first only focus on this flip flop, the first flip flop with the inputs J0 K0, and we note that. So this is the for J0 K0, this is the clock that is given to us, right? And since this is a negative edge triggered flip flop, we need to consider only the falling clock edges, which I have marked in the diagram here. Now, so what will happen at the falling clock edge? If J and K both are high, which is the case here, that output should simply toggle. So what is the initial output? Initial output is 0. Output will toggle at this clock edge simply, and it will remain constant. What happens at the negative, at the again the falling clock edge, J and K are again both are high, J0 K0 both are 1. So again the output will toggle. So Q0 will now toggle from 1 to 0. It will remain constant. Again at the next falling clock edge, J0 K0 both are high, so Q0 will again toggle. This time Q0 will toggle from 0 to 1, and this cycle will continue. It will keep on toggling at every falling clock edge because J0 K0 both are set to high. Now we have obtained Q0. Now let's shift our focus to this flip flop, the J1 K1 flip flop, right? So the clock to this flip flop is nothing but this Q0, and this is negative edge triggered flip flop. So for J1 K1, we need to find the falling edges of this waveform. So these are the falling edges of this waveform, right? So again we'll now try to plot Q1. What is the output Q1? In order to find Q1, since J1 K1 both are high and initial value is 0 as shown here. So at this falling clock edge, what will happen is that since J1 K1 both are high, Q1 will simply toggle. So Q1 will toggle from 0 to 1. It will remain constant. It will remain constant again until the next falling edge. So this is the falling clock edge for J1 K1, right? So what will happen? J1 K1 both are high again, and then the output Q1 will again toggle. This time Q1 will toggle from 1 to 0. Similarly, this is the falling clock edge for this flip flop, and again the output will toggle from the output Q1 will toggle from 0 to 1. So again this toggles, and finally this will toggle again at the final clock edge because J1 K1 both are high. Now we have obtained Q1. Now let's shift our focus to the next flip flop, which is this one, which have been marked J2 and K2. Now the clock to this flip flop is nothing but the output Q1. So we first mark the falling edge of the clock, which is the falling edge of Q1. This is the falling edge of Q1, right? And now we'll try to plot what is the Q2. So initially Q2 is 0. So Q2 will remain 0. Q2 will remain 0 until there is a falling clock edge. There is a falling clock edge. J2 and K2 both are high, as you can see here, and simply Q2 will toggle due to this condition. So Q2 will toggle from 0 to 1. It will remain constant. It will remain constant until it encounters another falling clock edge, which is this, and again J2 and K2 both are high, which is shown here, and so again Q2 will flip this time from 1 to 0, and it will remain constant. Now finally, now that we have obtained this waveform for Q2, now we'll shift our focus to the final flip flop, which is J3 and K3. And so again we need to find the clock for this, which is nothing but the output Q2. So we need to find the falling edge of Q2, which is this. There's only one falling edge, and we'll try to plot Q3. Q3 will again at the falling clock edge, J3 and K3 are high, which is true. So the output will simply toggle. So Q3 initial output is 0, which is given in the problem. It will toggle from 0 to 1, and it will remain 1. Now we have obtained the waveforms for Q0, Q1, Q2 and Q3. Note Q0 was the LSB and Q3 was the MSB. So if we populate this table here, note that at this junction all were 0. So in binary it's 0, 0, 0, 0. At this clock edge, here it's 0, 0, 0, 1. Right? In decimal it will be 1. And similarly, if you continue at time t1, Q0 is 0, Q1 is 0, Q2 is 0, while Q3 is 1. So it will be 1, 0, 0, 0, and in decimal this number comes out to be 8. That's why I told you, you can see that it's increasing in every clock cycle. This is what I meant by the 4-bit ripple counter. So we have obtained that the output is Q3 is 1, this Q3 is 1, Q2 is 0, Q1 is 0, and Q0 is 0. In the decimal, this value came out to be 8. So the correct option is B. Thank you for listening.